started. So today we'll be looking at learning from observations and introduction to inverse reinforcement learning. So that's going to be the topic. Before we delve into it, so a couple of announcements. So first announcement is with respect to the project presentations and the project. So what we did is we released some project feedback on the abstracts that you submitted. And the scores on those abstracts are not going to count towards your final project grade, but they're an indication of how much work needs to be done to make it into a good project. So happy to discuss your project proposals in office hours if you want to discuss, or if you got a low score, I highly recommend that you do discuss so that your midterm project proposal is much better. And the second announcement is with respect to class feedback, which is due every Thursday. And you will get feedback on the class feedback also. I mean, if you have some questions and so on. However, if the questions are, big questions or, warrant a discussion, then we would, always recommend you to come to office hours. So any questions on the projects? No? Okay. So, let's get started with today's lecture. So last time, what we discussed is learning from demonstrations, and we saw various methods, right? We started off by putting demonstrations in the replay buffer, and then we discussed, how we can train reinforcement learning with demonstrations. We looked at skill discovery and so on and so forth, right? But in all the previous discussion, what we were assuming is that not only does the agent has access to an observation of how the task is done, but also how the task is being done, right? So now what we're going to look at is how can we learn by just observing someone else perform a task without needing to teleoperate the robot. So we'll start with some challenges which occur in learning by observing. We'll see how we can overcome some of these challenges, have an introduction to inverse RL, and then develop how imitation learning can benefit by having some good models of how things work. So, one of the themes in the previous lecture was that behavioral cloning can be tedious. Let me just make sure this is being recorded. I don't see the, okay, it is being recorded, so that's fine, right? So one theme that we saw in the previous lectures is behavioral cloning can be tedious. And one way to overcome it is if we can build agents which can just look at other agents. For example, they can just look at YouTube videos and perform the task that is being demonstrated. So to put it more concretely, suppose a human is giving a demonstration over here by manipulating the rope. Now, typically, what we assume is that my system might have access to both the states of the world, but also access to robot's action. Right? Instead, what we want to move towards is a paradigm where we only have access to the robot or to just the states of the world. Right? We do not have access to the robot actions over here. So this is typically what you would get. If you are watching a video on YouTube, you wouldn't get a robot perform that task. But what you might get is, for example, in this video, Ashwin over here, he is manipulating this rope, and you are getting a sequence of images of a rope manipulation task. So just to remind that what we looked at previous lecture was learning from demonstrations of behavioral cloning. And today we are looking at observational learning, which means behavior cloning, but without actions. So now there are two setups that one can have. So one is a first person setup, and one is a third person setup. Now, what do I mean by first person and third person? So for example, consider this video over here, right? Suppose this person is demonstrating a task. Now I am looking at him, right? So that is one viewpoint. And the one viewpoint is the person himself looking at the task, right? So if I look at my own self performing a task, that is known as the first person viewpoint. Versus if I look at someone else performing a task, it's known as a third person viewpoint. And if you are getting videos from a third person viewpoint, you need to be able to generalize to a different viewpoint so that you can perform the task in the first person, right? Why is that necessary? For example, there's a kitchen or there's a cooking video that you watch on YouTube. You'll be observing a video in which the person looks as on your screen, right? But when you have stuff in front of you, you will be seeing it from a different viewpoint. But you still need to produce actions which can perform the task. So what you need to do is to generalize across viewpoints. Does that make sense? If not, pause me or bring up a question on the chat. The other challenge which comes up is that the human is manipulating, say, a bottle with his own hand, but a robot manipulator is different. So there is a correspondence problem that I, for example, cannot simply estimate the pose of the human hand and have the robot output the same poses, because I don't know how to map the human hand to the robot hand. One could try to learn this mapping, or there are other techniques that one could leverage. So there are two problems that we discussed in learning by observing. One is a correspondence problem, which is the first person, third person. The correspondence problem is that the manipulators are different. And second is the viewpoint problem, which is the first person and the third person viewpoint. And the third issue is going to be about the intent of the person. So for example, in this video, you see this person pouring a water bottle, or pouring water from a water bottle. So is the goal of this person to move his hand? Is the goal of the person to bring the bottle near to the beaker? Or is the goal to pour the water inside the beaker? So if I just look at the number of frames which are involved, if I just look at the number of frames that are involved where the water is being poured, that is much fewer than the number of frames in which the hand is moving. So if I am trying to maybe match something frame by frame, or get some gist of the entire video, I might infer that the task the human is trying to perform is to move the hand and not pour the water. It is because we have prior knowledge about the world that we understand that moving the hand is not an interesting thing. But what is interesting is the fact that water leaves the bottle and goes inside the beaker. And that is what we actually care about. So in a way, what we need to do is to infer the intent. And how do we infer the intent is an open challenge. And it's a question that we are going to look at in the course of this lecture. Are these issues clear? Any questions on these three issues? Nope, I don't see anything in the chat. So, okay, so then let's start with looking at, first of these issues, which is the viewpoint problem. So just to visually demonstrate the viewpoint problem, right? So this is the first person view, and this is the third person view, right? So third person view is typically what you would get if you are looking at a video on YouTube, someone is picturing the person, and the first person is how the world is going to look like from my own senses, right? In this case, my eyes. So how do we, learn systems which, if trained on third-person videos, can perform well on first-person videos? So one idea over here is that we want to learn feature representations which are invariant to the viewpoint. So, for example, suppose I have one demonstration of pouring a liquid into a cup from one viewpoint. Assume that we also saw the same demonstration from a different viewpoint. So V1 over here means viewpoint 1 and V2 means viewpoint 2, right? And xt denotes the image at time point t, and at time t plus k, we have the image at time point t plus k. So one thing we might do for viewpoint invariance is to have the following loss function, which says that features of viewpoint 1 should be close to features of viewpoint 2, where f might be a neural network which is taking as input the image x and outputting some features. And the question that I'm going to ask is this going to work? Is this, by work, I mean, is this going to lead to viewpoint invariance? Right? So let's do a poll on this and see, what people think. So I think you all have access to the poll right now. So let's, maybe give it 30 seconds and, think about the question or answer the question. So I think I'm going to close the poll, maybe in 5 seconds. So I see a couple of you have not answered yet. So I would encourage you, to, make your choice. Okay, so we're going closing in, 3, 2, 1. So let's look at, what people think. So most of you think that this is not going to work, and 5 of you think that this is indeed going to work. So among the people who think that this is not going to work, can you say why this may not work? I see something coming on the chat. Yes, so the first suggestion on the chat is, isn't it easy for the neural network to just make everything 0? So yes, so what we will have is a trivial solution where everything becomes equal to 0 and this loss function will be minimized. So what we're going to do is to force this loss function to not have a trivial solution, we're going to add a penalty term, right? And what this penalty term is going to say is that the representation of an image at time point t should be different than the representation of the image at time t plus k, right? So now I want to separate out the representation of images which occur far away in time and which this term is doing, right? The second term that you see in the orange box is trying to impose that constraint. And why is that? Right? For example, if the representation at t and t plus k became equal, then this value is going to be 1, right? Because this becomes 0, this will be 1, which means that I'm not looking at the minimum, right? So if I want to minimize the whole loss function, then the distance between the features at time point t and time t plus k better be greater than 1, right? Where one is an arbitrary constant, and you can choose it to be C, right? You can just scale everything by C. So you could have it as C, right? So what you're saying is I want to have a margin, and I want the distance between features to be greater than a margin. And this is what constitutes or what is known as a triplet loss. Why is it a triplet loss? Because I have one image, which is my anchor image, and then I have one frame which from a different viewpoint, which I call as a positive frame. Why is it positive? Because I want the embedding of the anchor and the positive to match up, and I want the embedding of the anchor and the negative to not match up. And this loss function or this method was proposed in the paper Time Contrastive Networks by Pierre Sermonnet in 2017. And this TC embedding is a short form for saying time contrastive embedding. So a question that popped up in the chat is, isn't something similar done in LLP problems as well? Yes. So I think if you look at word2vec and some of other embedding learning techniques, they end up doing something similar. So I think what you will see is the form of the loss function is quite similar across a bunch of tasks. What really matters is how do you choose positives and negatives. Right? So over here, they're choosing the positives and negatives in a manner that allows you to get viewpoint invariance. So let's look at how well this system does, or this feature learning does. And the way to do this is that we are going to take a third person video and find the nearest neighbors in the feature space of videos in the first person. Right? So if my feature embedding is good, then the video on the left should be aligned with video on the right. Right? But if my feature embedding is not good, then when I do nearest neighbors, then I'm going to get bad results. Right? So if you look at what happens over here, as we are finding nearest neighbors for this particular demonstration, this is what we end up finding. Right? So what this means is the system has learned something which is viewpoint invariant, and one could compare this to some baselines. And what you'll find is that the baselines don't end up performing as well. For example, the single view TCN starts scoring even before the observation is done, right? Now here is one more example where showing that we can get viewpoint invariance on this scoring task. Okay, well, fair enough. So what we're able to learn is a representation which is invariant to viewpoints. But how do I actually use this to learn a policy to perform the task? So, one strategy is that we could go and define a reward function, right? And how we're going to define the reward function is to say there is a demo, and I have feature representation V1 to VT of the frames that were in the demo, right? And where is this feature representation coming from? It is coming from the time contrastive network that we just learned. And then we have the feature representation of T frames coming from the robot's viewpoint. And I'm going to define my reward function to minimize the L2 distance. And then you see this other term beta. This term sometimes helps you, this is, making the reward function, work better, right? It ends up making the loss function slightly more robust, or the reward function slightly more robust. So we have this reward function, which is putting the demonstrations and robot observations close to each other. And then, we can leverage
The
this.
second step of our approach is to use reinforcement learning to learn.
We can then leverage this TCN network that we have learned to generate a reward function. And then we can do reinforcement learning to optimize this reward function, right? So let's see, what happens. So initially, the learn policy is pretty bad. And then over time, what you will see is, that the system is going to be able to perform the task, right? So a couple of things to notice, right? The robot doesn't have liquids. I mean, typically people don't do that because having liquids around robots is, not fun because it might, go in the circuitry, right? And the other thing you should also notice is that the robot starts off with the cup in the hand, right? So it's not picking up the cup. So, in some ways, this is, a reasonable demonstration of how you can use a good feature space to define a reward function, right? So just to tie it back in, right? So remember in the reward design class, we looked at an example where we had an agent which has to go around the wall, right? And what we found was that just using the L2 distance was not a good distance function because the agent can get stuck against the wall. And what we required was to have a good distance function, right? Which was the A star distance function in that case. Or more generally, one would need to learn that distance function. And this work is just showing an example where we have learned a good distance function by learning the feature space. And we can use that feature space and the reward function defined with help of that feature space to perform the task at hand. So any questions on this part? So one question is, what if W and V are essentially the same thing but displaced in time from each other? Yes. So, what is happening is, if you look at this, the equations over here, W is what you are generating over time. Right? So what you would want to do is to match the demonstration one by one. Right? So the robot could do the task in many, many different ways, right? I mean, it could do it faster than the demonstration, it could do it slower than the demonstration, and eventually you will get the same result. But out of these many possible solutions, this reward function picks up one of those solutions, which is where the robot tries to match the demonstration frame by frame. Does it clarify your question, Dhruv? Yeah. Okay.
The second step of our approach.
So now, that also, leads to a, good point or an interesting point to ponder about, right? So these kind of reward functions are forcing me to match the demonstration, frame by frame. Can you think of a scenario where this might not be a good idea? That I do not want to match things frame by frame. But just to repeat, what do I mean by frame by frame? I mean that if in a demonstration at time step t, the cup is at a certain position, the robot also wants to put the cup in the same position at time step t. And this is what this reward function is encouraging the system to do. And the question is, when is this a bad idea? So I'm getting a couple of suggestions on the chat window. So one of them is when pouring a liquid with different density or viscosity, right? Because then you need to pour for a different amount of time. So if you copy it frame by frame, you're not going to achieve the task, right? Which is the example of when the testing environment is different from the observed environment, right? This is what was pointed out by, I think, Dhruv on the chat window. So instead of actually copying frame by frame, what you want to do is to infer the intent, or what is it that the agent is trying to do, and then I can go and perform the task. So, for example, one of these works was on, door opening. So the setup is the following. You have this robot which is trying to open the door. Now over here, if you see, there are sensors which measure when the door, is open. So you can use this to evaluate whether the door opening is successful or not. And this is, the robot that we have. Now, in order to communicate, what the task is, what these people did is to give some demonstrations of the robot performing the task, but these demonstrations were not very good, right? They succeeded only 10 to 20% of the time. And there's a term which is kinesthetic demonstrations. What does this mean? This means the kind of demonstrations in which you manually move the robot. And that is the term for those kind of demonstrations. And now the hope is that given, somewhat, poor kinesthetic demonstrations, and, can we then leverage them and do some trial and error in the real world to do well on the task? So this is, one problem setup, that you can have, right? So maybe you give some demonstrations, and, so there are two kind of demonstrations you have given, right? So one is where the human is, opening these doors, and what this is communicating is what the task is that the agent needs to do, right? And this is what we want to infer from it. And, we might also give, move the robot and provide it with some, initial seed, which was, these bad demonstrations which were given, right? And, these demonstrations, are pretty much trying to overcome the exploration problem, for example. And then, the question we can ask is, will we be able to go and solve the task? And what this work, pursues is an approach where they try to learn a reward function, right? So what is a reward function? So reward function is a succinct description of the intent, right? And then, go and optimize that particular reward function to perform door opening, right? So what we're going to look at in, a large part of this lecture are what kind of algorithms go into inferring, these kind of reward functions, which help us infer the intent of what the person is doing. But before we, dive into it and dive into a completely learning-based method, it's worthwhile discussing some alternatives to infer the intent. And to do this, let's put on a computer vision hat, right? And consider this particular scenario where we are trying to cut vegetables in the kitchen. So I have a YouTube video of someone cutting the tomato over here. Now we have good object detectors. So we could use those detectors to figure out where the tomato is, where the hands are, and where the knife is. Right? So we're imposing a prior on what are useful things in the environment. And we do this by having some object detectors. Right? So given that image, we can have CNNs, which are predicting what kinds of objects are there. Now we could also impose additional prior knowledge. For example, I can try to classify which kind of grasp the human hand is doing, right? Or what kind of manipulation the human hand is doing. So we can have a library of different kinds of manipulation a human hand can do, right? For example, it could be pinch, or it could be like closing the fingers. It could be grasp, it could be a power grasp, and so on and so forth. Now, why would you do this? You would do this to solve the, the correspondence problem, right? For example, if you know that we need to pinch the fingers, then you can have a predefined policy on the robot which pinches the finger or which grasps the object, right? So now we know what objects are in the scene, and we know what kind of manipulations are being done on those objects. So what we can now do is, given the objects and the kinds of manipulations we have, one could try to find you know a coherent description of what the task was, right? For example, the left hand performed a power grasp to hold the knife, right? And the right hand, using a particular kind of a grasp, was holding a tomato. So now I'm not going to discuss these kind of methods in this particular class, but the reason for bringing this up is so that you understand, and to also give you a perspective of how people have approached this problem from a non end-to-end learning framework, right? So what they would do is they would develop a taxonomy for action types. They would identify what are the important objects, right? Then they would get things like left hand, right hand, what are those grasp types, what are the objects that they're manipulating, and what is the action they're taking, right? And then you would get this information per frame, and then you would convert it into a parse tree depending on some grammar that you end up defining. And now these things, left hand do a power small grasp on a knife, are some things which I can hand code on the robot, right? So I can hand code a small grasp, I can hand code a precision grasp, right? And then the robot can execute it. So these kinds of approaches have been the dominant approaches when people have attempted, for example, to go and look at videos, parse them, and then perform the task that is happening in the video. Now, what has improved in the past 5 to 7 years is that the object detection technology has improved quite a lot. Human hand pose estimation has improved quite a lot. And because of those successes, some of these techniques, work much better than what they used to work, maybe 10 years ago or 20 years ago. And I mean, learning from videos is something which researchers have been interested for an extremely long amount of time. So, something, if you want to look for more references, you should look up this paper and look at the papers which this paper cites and, papers that cite it. It's a good canonical example of how you would do it from a classical perspective. So we are not going to, take this perspective for now. The perspective we are going to take is, where we are going to assume minimal knowledge that the system has, and how can we perform the tasks then, right? So we just have a video, we need to learn to perform the task, right? So the first approach that we saw was I can learn a good feature space by doing some feature learning and then define a reward function, right? But the problem with defining a reward function is that I was encouraging for the robot to match the demonstration exactly. But if the test environment is different from the training one, that becomes an issue, right? So what we want to go towards are methods where different actions are required from the same state to get to the goal, right? Or maybe the actions are completely different and I can't match the actions, but the final goal is the same, right? So just to give an intuition, right? For example, consider I want to move this blue ball to this green location. It's over here. If I give a demonstration, it would go from the left and then go to the green. But if I change the environment to have the wall like this, now all my actions have to go towards right. And so if I do any kind of behavior cloning or frame by frame matching, it is not going to work. Similarly, for example, I have this, four-legged agent over here, and I'm trying to learn a policy to make it walk. But now suppose I cripple the legs. Right? So now again, there's a discrepancy between my training and testing environment. So if I know the intent, it's going to be easy for me to adapt. But if I don't know the intent, this is going to become hard. Right? A practical example of this is, self-driving cars. I mean, if we are going to have demonstrations of how to drive, I cannot copy the actions exactly because every traffic scenario is going to be different. So how do we approach this? So the first idea is going to be that instead of just fitting the actions, we will try to learn the reward function and then find the appropriate policy, right? Because the hope is the reward function is going to generalize across environments. And then for a new environment, I can find the policy. So, so traditionally in reinforcement learning, we have rewards and the environment as inputs, and the RL system gets me a behavior, right? Now we are going the opposite way, right? From the behavior and the environment, I want to infer what the rewards were. And so that is what is known as the problem of inverse reinforcement learning. So let's consider an example, which is the mountain car, which you might have encountered in your homeworks. So you have the car over here. It needs to go to this goal. Now suppose the state is the x position and the velocity of the car, and assume that we are provided with a few expert demos of this task. And I have some features of the state, which can be functions of x position, right? They could be x, x squared, so on and so forth. And the general problem is going to be following, right? We have some expert policies. We have policies that we want to learn. But instead of directly copying the expert, we are first going to estimate a reward function and then use this reward function to learn the policy. So to go about it, first thing we're going to assume is that the expert is optimal. That the expert demonstration is the best way to do the task. That's the first assumption that we are going to be making. Now, if we make that assumption, what that means is that suppose I have the Q function of taking the expert action. The policy that I find should also have a Q function which is close to the expert. And if I'm able to find this, I should find the optimal policy because I'm assuming my expert is optimal. Now you might be wondering, where is this Q function coming from? This is coming from the rewards that we estimate, right? So typically in reinforcement learning, you would assume the environment gave you the reward. But now, instead of the environment, think there's some function f with parameters alpha that we are trying to learn, which is going to provide the reward. And we can calculate the Q values with respect to those rewards. But this, straightforward implementation has an issue. And the issue is that there can be trivial solutions, right? For example, I can set QS, A to be zeros. Right? So what can we do to circumvent it? So one idea which has been used and was in the foundational paper for inverse reinforcement learning, the reference of which is in the bottom right of the slide, is to say, we want to learn rewards or Q values that penalize deviations from the expert. to say it, more concretely, I want to find the action which gets me as close to the expert, but the reward function that I am trying to find is the one that is separating the expert demonstrations from other policies. So what is happening over here, right? So suppose I come up with a reward function, and then I find the policy that maximizes the reward function, right? And suppose that is my q s comma a. Now, in order to make the expert be special, or to make the expert be optimal, what I'm going to say is, find me a reward function so that the expert trajectories have higher rewards than any other trajectory. So let me make this, more concrete. So, suppose, we take this term over here and we rewrite this. Now we rewrite this, we take the min inside, so it becomes a max over here. Because if I choose the action which has the maximum Q value, that is going to be as close to the expert as possible. And then D is some distance function. So what this is saying is, so find a reward function so that the expert trajectories have higher reward than all other trajectories. So in a way, what we're imposing, or we are saying, because I don't have access to a reward function, I'm going to define rewards as a quantity. So that if I execute expert trajectories, that quantity should be high. And if I execute anything else, then that quantity should be low. Right? And now we are going to, and that quantity is going to be my reward function, right? But the problem is that we cannot evaluate the reward function for all possible trajectories. Right? We can only evaluate the reward function for a few trajectories that we can sample. So instead of saying this max over all actions, right, a more practical thing to say is, my sum of rewards from my expert policy should be greater than the sum of rewards from all the policies that I have tried until now. Right? Which means that maybe I've evaluated K policies, so I should be better than any of those K policies. Which means that this loss function that I have, gets rewritten as the following form. Right? So instead of doing over all possible policies, now I am optimizing this over a set of finite policies, or a set of finite trajectories which we got by executing these K policies. So the one question you might ask is, how do we get these trajectories in the first place? So, the way we're going to do this is, suppose we had this loss function that we were trying to optimize. Right? We optimize this, and when we optimize this, we're going to get a new reward function. And then based on this new reward function, we're going to optimize the policy. And then we're going to keep on iterating between finding a new reward function and then optimizing the policy. And so what I'm doing is, I start off with a random policy, I execute it, right? And I start off with a random reward function. Why is that? Because initially my parameters alpha are random, right? So I have a policy to execute, and I have my expert policy, which I already have access to states and actions, right? Now I try to modify my reward function so that the expert trajectories have higher rewards than the policy that I just executed. Right? This gives me a new reward function. Now I try to find a policy that is able to optimize this reward function. So the hope is this is going to get us closer to the expert. Right? But if I don't come close to the expert, then I can find a new reward function, which is going to be able to differentiate my expert policy from the policy that I just executed. So this process can only converge if the value function of the policy that I am executing is exactly the same as that of the expert, or that there is no way to distinguish expert trajectories from the trajectories that I am executing. Right? Only at that point will this optimization converge. So typically, we call this loop of finding the reward functions as the outer loop, right? And we can solve this using SDD. And when we use the reward function to optimize the policy, this is typically called the inner loop, and we can solve this with RL. But this should also make you really pause and think, because if we have RL as an inner loop, you should be thinking that if RL is in the inner loop, the RL by itself is very computationally expensive as a method to learn policy, and it has high variance, right? So if RL is a subroutine of some other method, that method is also going to be even more computationally expensive, and might end up having even a higher variance. So before I go ahead, I want to pause and see if there are any questions on how do we find reward functions. Are there things that we should maybe go over and look at once more, or is did you get the intuition behind how do we learn a reward function? Any comments? I mean, if maybe if you got it, maybe you can say yes on the chat. If you didn't get it, you can say no on the chat, and that way I'll know if I lost you or are you still with me. I think this is the the foundational part of inverse RL, and it's important to understand this. If I went too quickly or something was not clear, we can spend some time discussing that. Okay, so one comment was, can I summarize this again? Right. So, okay. So for the distance function, for a moment, let's assume this distance function is just an L1 distance or an L2 distance, right? So what I'm trying to measure is the difference in my value functions, right? That is how the distance function, let's assume that for now. So, okay, initially, what do I have? I have a set of expert policies, and that's the only thing that I have. Now, I want to estimate the reward because we are trying to infer the intent of those expert demonstrations. So I want to reduce the expert demonstrations into a reward function, right? That is the goal that we have. Now we cannot do supervised learning over here because no one told me what the reward function is, right? So it is something which we must infer from the set of expert demonstrations that I have been given. So what I'm going to say is, let me assume the reward is some function of the state with parameters alpha, right? And we want to estimate these parameters alpha. And if you're able to estimate them, then whatever output is going to be it, I'm going to call it a reward. But the question is, what is the supervision to estimate these parameters alpha? So the assumption that we make is that suppose I roll out many trajectories which are not from the expert. I want the reward of those trajectories should be lower than the trajectories that the expert has, right? Which is this loss function over here, right? Which is saying that if I'm maximizing it, it means that I want to increase the value of my expert as opposed to any other policy which is there. So I can optimize alpha to maximize this function. And the output of this is going to be a reward function. But the question you might have is, well, you said the expert should be better than other policies. But how do I get these other policies? If I just take random policies, maybe those policies are so bad that the reward function is not very meaningful, right? So could we try to improve the set of other policies, right? The way to do this is you take this reward function and then you find the policy which maximizes this new reward function. Now I say my expert should be better than this new policy that I found. Right? So if I end up doing this iteratively, at some point, I should get the same policy as the expert, and that is when this optimization is going to converge. Right? And at that point, whatever the reward function I have is going to be a reward function which is consistent with expert demonstrations. Does the summary clarify what we are doing over here and how are we inferring the reward function? So maybe I can have a show of yeses and nos on the chat. People who got it, and maybe if it is still something is unclear. Okay. Yes. Yes, I think Ayush, your comment is to the point. That's exactly what we are trying to achieve over here. Okay, so I will move ahead, but if you have questions, please stop. So first let's assume a simple case where rewards are linear in features. Let's suppose I have defined some features phi of s, and I'm going to assume that my reward function is linear in these features, right? And we are still trying to maximize this quantity. But now, still the problem is that there are many reward functions that can satisfy this criteria. Right? So how do I, choose one out of the many, many possible different reward functions which could be there? Why is this? Because we know that for a given reward function, there are multiple trajectories or multiple policies which can have the same reward function. Right? So if I just give you a bunch of trajectories and I say, find me a reward function, I can take the reward, I can add some number to it, I can square the reward, I can cube the reward, right? I can do a polynomial of the reward. All of them, have the same, optimal policy, but also many, many policies which are also optimal for that reward function, right? So, there are, given a set of trajectories, there are many reward functions which will satisfy those trajectories. So how do we pick one of them? This is exactly where in machine learning we use regularization. So one regularization that we can use is that these alphas which are there should be small, which should encourage learning of simple reward functions. Right? So if you're familiar with lasso in regression, when you put an L1 penalty, which is the penalty being put over here, this encourages sparsity. So what this means is, maybe I want to use as few features as possible to learn my reward function. And in this case, where the reward function is linear in features, we can solve this using linear programming, right? Because this is a linear program that we can solve. And just for clarity, this index 1 to D means there are D different features. Right? For example, in the mountain car, the feature could be the position and the velocity, right? So in that case, D is going to be 2, for instance. So let's see an example from this paper. And so this was, maybe we got these demonstrations, which makes it pretty clear that the goal is over here. So the ground truth reward function is this, right? So +1 reward if you reach the top right, and the reward of 0 everywhere else. And this is the objective function that we are trying to maximize. And I just put the objective function in the Lagrange form, where instead of the constraint, I put it as lambda times the constraint. Now, if you put lambda is equal to 0, which is that I'm not putting any regularization, we end up getting this reward function, which is somewhat complicated. Whereas, if we put lambda as 1.05, for instance, we get a much simpler reward function, which, for example, over here is closer to the ground truth reward function. So, similarly for, mountain car, we can end up, getting, like a good reward function. So if you see the reward function increases as you go closer to the goal, it's pretty constant in the middle, but it's also high as you go far away, right? Why is it high? Because you have to climb this mountain or you have to climb this pit. Then if you go behind, it will give you acceleration to cross this pit, right? So the states which are in negative X actually have high rewards. So the method is, able to figure out a reward function which explains the behavior over here. So any questions over here on these examples? So Ayush, to your question of how unstable is this two-loop process, it is extremely unstable. So if you thought, RL was, an established method, which we, now know is not. I mean, there are a lot of things in RL which cause problems. For example, variance is a big problem. IRL is even worse, right? Both in terms of reproducibility of results and also the amount of variance you have and how computationally expensive it can be. So it's pretty much a very open research direction, even more open than reinforcement learning.
Got it. I mean, like, are there like specific methods to do like optimization in the outer loop? Because like it's trying to maximize a function, which I don't know, like, usually it's not the best way. Like we try to finding minimas for function is usually like more stable. So like people do like one by loss functions and stuff to sort of convert the maximization problem into minimization.
I mean, you can just do a negative sign of it, right? So maximization, so trying to maximize is not the thing which is causing instability, right? The thing which causes instability is that the variance in RL is high.
Okay.
Right? So now you are relying on the RL policy to estimate a reward function, right? So the variance is high. That means that the reward function estimate you're going to get is going to have higher variance. And then again, you optimize that with RL, right? So yeah, you have this loop of where you're feeding, back noise and the noise is going to increase in the system.
Oui, bonjour. J'ai remarqué en regardant un peu mes comptes des derniers mois qu'il y avait une transaction récurrente que je pensais qui n'est pas effectuée par moi.
Does it make sense? Does it make sense, Ayush?
Yeah, it makes, yeah, thanks.
Okay. Any other questions? So Andy, I mean, this is a good question. What are the trade-offs between behavior cloning and IRL? So, in IRL, we're trying to estimate a reward function, which means that we will be able to transfer to a different environment, which is very hard to do with just behavior cloning, right? The thing that works in favor of behavior cloning is that it is much simpler to implement. It's much more stable because it is supervised learning. It doesn't have this inner loop, outer loop, right? And the other thing that people have found out that we'll look very shortly is that with IRL, if it works, you require fewer demonstrations, or you're able to learn a better policy with fewer demonstrations as opposed to behavior cloning. So that's how you can, behavior cloning, simple to implement, but cannot generalize as well. IRL complex to implement. If it works, it performs better than behavior cloning and is able to generalize. So now, let's, move ahead and see a slightly different interpretation of the same phenomena that we discussed, or the same IRL phenomena that we have been discussing. So assume again that my reward function is, a linear function of the features where this W star is for the optimal reward function, which is unknown to us. Right? And we are trying to estimate the value function, and the value function, this is how we write it, a value function for policy pi. Now, if features are linear, I can write my reward function as W transpose phi, and I can bring out W. Now the term which is over here is what I can call as feature expectation, which is what is the expected feature in the future if I run the policy pi. Just like the value function outputs the expected rewards, this term mu pi is saying what is the average feature if I run this policy. And suppose we are also able to estimate the feature expectation of the expert, right? Suppose I got M policies from the expert, so I can find, what is the average feature in the expert policies. And one claim we are going to make is that in this linear case, I can just find a good policy by satisfying the following condition, that the policy which I'm trying to find, pi tilde, its feature expectation should be close to the expert's feature expectation, right? That is, feature matching is sufficient to find good policies. So instead of trying to infer the reward function and then optimize the reward function, we can also think of IRL as trying to do feature matching. And this equivalence is valid in case of linear reward functions. And we can prove it quite easily. Right? Suppose if I look at the difference in my rewards, right, which is my expert policy reward and the policy that I'm trying to find its reward, right? I can write it down as W transpose mu and W transpose mu of E. Right? And I can use linear algebra to take W out. Why is that? Because of this particular inequality. And if I am willing to constrain W to be less than 1, then if my feature, if I'm able to match features within a bound of epsilon, it means that the rewards of those two policies are also very close to each other, right? So the takeaway is, in case of linear, when the policies or when the reward function is linear in features, I do not explicitly need to compute the reward function, right? I can just think of them as doing feature matching. And those two things are equivalent. Right? It's just a different interpretation. Now, this is what was popularized by this paper, Apprenticeship Learning, published by Peter Abel back in 2004. So let's look at algorithmically how it works. So initially, we have a random policy, and we execute this random policy multiple times or single time, and we find the feature expectation. Right? Then we calculate what is the difference in feature expectation between my expert policy and my current policy. And then we try to find a W which maximizes this feature expectation, right? Which is similar to what we were doing previously, right? We first found, we had two policies and we were trying to infer the reward function which maximizes the difference between the expert and the current policy, right? So this is the role that W is playing over here. Then what we look at is, if the difference in rewards of my expert policy and the current policy is less than epsilon, then we're going to terminate, right? Makes sense. If it is not, then I can use the RL algorithm to compute the optimal policy with this as the reward function. Then, now I have a new policy, I can compute the feature expectation and repeat this loop over and over again. So in a way, we just described the same thing that we discussed, in the previous part of the lecture, right? But I think the takeaway is the interpretation that feature matching and finding the reward function are equivalent when the reward function is linear in features. Right? So, so the other, so this, interpretation, you can, some people think of it as a max margin perspective, right? Where I'm trying to say that the reward function of my expert policies is larger than the reward function of my current policies by a margin of t, right? It is equivalent to saying, find a reward function R so that the margin between the expert and the current policy is at least t. Again, intuitively, find a reward function so the expert is better than all other policies by a margin t. Right? And in this case, we can solve this using SVM-like solvers or quadratic programming solvers. Why QP? Because now we have this L2 constraint that we have, right? If we had the L1 constraint, then we could use linear solvers. If you have the L2 constraint, we'll have to use quadratic program solvers. So if you are familiar with SVMs, support vector machines, you can see an equivalence between the reward function that we just wrote down over here, or sorry, the objective function we wrote down over here, and the objective function which SVMs have. Now we can go and compare, the IRL approach, with other approaches to learn policies. So on the y-axis is the performance. On the x-axis is the number of trajectories. Right? So this blue and the green line are two variants of IRL. And the blue line is when I'm trying to mimic the expert. So what you find is that if you're directly trying to mimic the expert, that performs, or it requires more trajectories than if you're doing IRL. And some of the interesting applications of apprenticeship learning, so one of them which became popular,
What helicopter does.
is this demonstration of helicopter acrobatics. So what is happening over here is this person that you just saw So they are giving, these demonstrations of flying the helicopter, right? So this helicopter is doing, some kind of acrobatics. Based on these trajectories, we collect a reward function and then make the helicopter do the same things, right? So why is this problem hard for learning from demonstrations directly? Is because, the wind might be blowing in waves that you don't know, right? So, and the state of the helicopter, could also be different. So because the environment can change, directly doing behavior cloning may not work as well. Versus if you learn the reward function and then you optimize it, you might end up doing much better. A second example is in quadruped locomotion. So here is a little dog robot, which is a precursor to Boston Dynamics spot robots, almost 15 years back. And what we want this robot is to maybe go over this terrain. And on the right, what you're seeing is the height map, right? Where white means that it is, it's like a big bump. And if it is black, it means it's flat, right? The bumps are, shown over here. Now, for these kind of systems, giving demonstrations is hard. Why is it hard? Because the degrees of freedom are very high, right? There are 12 degrees of freedom for legs and 6 for the body. So there are 18 degrees of freedom. So it's very hard to, manually, control this robot so that it can walk across this terrain. So what do we do in that setup? So one solution is to give hierarchical demonstrations. What do I mean by this? So first I can give high-level demos which say how the center of mass of this agent should be moving, right? Which is, maybe this trajectory where it kind of walks through flat parts mostly is going to be easier than trying to, maybe crawl up on this up and then go down and up and go down, right? So I can give a demonstration by specifying how the center of mass should be moving. Then, the robot needs to plant its foot legs. So now what I can do is I can now give demonstrations on where I want this robot. For example, the green dot, where I want the robot to place its foot. Right? So I can give some low-level demos. So in cases where demonstrations are harder to give because the state space is big, I can decompose the problem at different levels of the hierarchy and then give demonstrations. Now, this was, what was the method used in at least one version of this video of this quadruped crossing, this terrain. So we have not gone into detail of this paper, but if you're interested, the reference is there. Feel free to look it up. I mean, I'm hopeful that you'll be able to understand what the paper is doing, given the context of the class. Then there are a couple of more concepts in IRL. For example, max entropy IRL, then guided cost learning, GALE and AIRL. The last three, take what we have learned until now and remove the assumption that we have linear features by putting in deep learning over there. And max entropy IRL is one more idea where you can think of maximum entropy as a regularizer, which helps me choose one out of n different reward functions. Right? Just as we use the L1 penalty to choose a simple reward function, we might as well use max entropy as a regularizer. So this is something that we're going to see in more detail in a future lecture. Right? And one thing, which I will, just briefly mention to maybe, get you thinking. So, in the previous lectures, we looked at standard behavior cloning in Dagger, where we had the expert policy, which is pi of x, and we had the policy that we were learning, which is pi a of s, right? And what we were optimizing was this forward KL. Now, for a lot of deep IRL methods or IRL methods, the ARL and GL are examples of that. What you'll see is they are optimizing the reverse scale, right? So where I'm trying to match the feature distribution, right, where rho is distribution of visited states and actions. Let's think of this as what we were looking at feature expectation. So when I'm matching the feature expectation, I end up using reverse scale. So that is one more mathematical interpretation of what is the difference between behavior cloning and IRL. One is forward scale, one is reverse scale. Now, this is something to maybe ponder about, and we will look at more detail about Gale and AIRL in a future lecture. I mean, we need some background for it, and once we do it, then we'll come back to these topics. Any questions or any comments? No. Okay, so let's march a little bit more ahead. So we started this lecture by saying that we want to learn from observations. For example, when the human performs a task, but we don't have access to actions. So I'm going to talk about one more method that we can leverage to perform this task. If, for example, I could have this human demonstration, right? And now if my goal is to pretty much say copy the human demonstrations, then what I need to do is I can take a pair of images, say IT and IT plus 1, and to copy the demonstration, all I need to figure out is what is the action I need to execute to go from image at time step t to the image at time step t plus 1. So essentially what we want to learn is an inverse model which can map a pair of images to actions. If we have such a model, then given a sequence of images, I can apply this model iteratively and then execute the task at hand. And then I could use the same model and do different tasks, right? For example, I might configure ropes in many, many different configurations. So, how could we do it? For example, so the question is, how do we learn that model? So, for example, we could have this robot which is collecting data on its own, right? So it picks up the rope and it keeps it. It picks up the rope, it keeps it. It keeps on doing this process for a long period of time, collecting a data set. Essentially, we have the rope in a particular configuration. The robot executes an action. We get the rope in a new configuration. And then we are going to leverage this data to learn a model. And the model we're going to learn is we're going to take my image xt and xt plus 1, and I'm going to try to predict the action over here. So, so now once this human gives a demonstration, I can use this model to go and parse the demonstration which the human has provided, right? For example, over here, again, is a demonstration of this person demonstrating tying a knot, and then you can go and execute tying a knot by watching this video demonstration. And what you can show is that if you were using no imitation learning on the task, you get some performance, but if you do use imitation learning, your performance increases. But the takeaway over here is that a human provides a demonstration, which is essentially a high-level plan, right? And because agent has a model of how the world works, it can leverage this model to execute a sequence of actions which can complete the task, right? So in a way, having some model of how the world works can also help us learn better from videos or from demonstrations that have been given. So one thing that we will be looking in the next few lectures are how do we do model learning, right? How do we leverage these models to solve sensory motor tasks in a more data efficient manner, but maybe also use these models to perform imitation learning or learning by observation, as we saw in this work that I presented to you. So now, one question, which also comes up is, we talked about this, robotic agent collecting its own data, right? So over here, the robot did some experiments, which is, moving the rope around. We learned the inverse model. Then when the human gave a demonstration, we were able to perform actions to execute this demonstration. But a natural question comes up is, how do I collect interesting data, right? So, if my data collection strategy is random. Now, what do I mean by random is I pick up a rope at a random point, then I move it by a random amount on the table, right? So if I end up doing that, I will only visit states, which are close to my starting point, right? So I might only come to states which are very, very close. But suppose, I want my system to go and tie a knot, right? Then instead of exploring these kind of states, it might be more useful to explore states in which are closer to how a knot might look like. But the problem is, just by performing random exploration, it's hard to go from this state to this state. So what do we do? Right? So one possibility is a human can come in and the human can provide a sequence or a set of images which the human thinks are interesting or good images or good states which the robot should explore around. And then the question becomes is how can the robot bias its exploration from the state it is in to the states that the human has provided, right? So this is maybe, think of it as learning by observation in a slightly different setup, right? So until now, what we looked at was, first we looked at we have access to both states and actions, and then we were doing, behavior cloning. Then we discussed that, okay, if you don't have access to state and actions and just states, what can we do in that case, right? And now we are saying, well, I'm not even going to show you a complete demonstration, but I'm going to just give you, some interesting states. So the human over here is just trying to bias the exploration of the agent rather than telling it how to do the task. And by biasing the exploration, it can lead to more interesting data collection. So this is, one aspect that we will touch more about on the lecture in exploration. But for example, how could you go, towards this particular goal image, or not a goal image, but an exploratory image the human has provided? One mechanism is, you have the inverse model that you have learned. So instead of, performing any action, what you can do is, I can take these two images, put them in the inverse model, and hope that the inverse model is going to give me, some actions which take me close towards the state which the human provided. And, turns out if you do, some of these things, you can improve the performance even more to 60%, right, on this task. So why am I telling you about this? I mean, the reason I'm telling you about this is that if you think about learning by observation, you should think at 3 levels. One, when I have access to state and the actions, how do I get the actions? Either by kinesthetically moving the robot, by virtual reality, by having these, kind of gloves that we saw, or by having hand tracking and so on, right? Other is YouTube, where I only have access to videos. And third is where I just bias the exploration of the agent, right? Then the big problem with behavioral cloning is that we try to match things, frame by frame, which becomes problematic when the environments are changing. And that is where, inverse reinforcement learning comes in. So hopefully, some of this will help you get a more holistic picture of how we can leverage human demonstrations or videos of humans performing a task to get our agents to perform more complex tasks. Right? So with that, I'm going to end, and we'll look at more advanced models.